Hi, let's continue our discussion of stability in control systems by looking in this video at how we can determine stability. Okay, in the previous video, we said that the necessary and sufficient condition for stability is that all the poles of the system transfer function lie on the negative, have negative real parts. So they lie on the negative side of the imaginary axis. And so, how are we going to evaluate stability? Basically, by looking at poles of the system transfer function. But in some cases, looking at the poles of the system transfer function becomes quite complicated. Let's say you have a fourth order system and you have a fourth order polynomial. Finding out the poles of that system may be very, very complicated. So, people have developed easier ways of finding out whether the poles are on the have negative real parts or not. Okay, so let's start by looking at a first order system. So let's say the first order system has a characteristic equation as shown here. Okay, now if the roots of the characteristic, if we find the roots of the characteristic equation, that gives us the poles of this transfer function, right? So when are these poles going to be negative or will have negative real roots? The answer is fairly straightforward in this case, isn't it? Um, the system will not have any poles with positive real parts. That is, the system will not be unstable if the coefficients of the characteristic equation are of the same sign. So if a1 and a0 are of the same sign, then all the poles will have negative real parts, and therefore the system is going to be stable. And you can just look at this very easily, right? Because if both of these are of the same sign, then S will be equal to minus a0 over a1, and the pole is going to have a negative real part. Now, similarly, for a second order system, the rule is fairly straightforward. The system will not have any poles with positive real parts. That is, the system will not be unstable if the coefficients of the characteristic equation are of the same sign. So if a2, a1 and a0 are all of the same sign, then all the poles, none of the poles are going to lie on the positive side or will have positive real parts or will lie on the positive side of the imaginary axis. So if all the coefficients are of the same sign, we can assume that the system is stable. Okay, for a higher order system, higher order than 2, things become slightly more complicated. And we use what is called the Routh-Hurwitz criterion to evaluate stability. Now, I just want to repeat this, okay? For the first order or the second order or for a higher order system, to evaluate stability, all you need to do is find the roots of this characteristic equation. The roots of the characteristic equation are going to be the poles. And if all the poles have negative real parts, the system is going to be stable. But finding the roots of this equation is quite complicated. So we are trying to make easier rules, right? So for a second order system, we said, well, you could evaluate the roots of the characteristic equation. It's not very difficult, but it is much easier to just look at the signs of the coefficients and say, well, the system is going to be stable. So we are trying to find out an easier way than actually evaluating the poles of uh, equation. And this becomes especially useful when you have third order and above systems, right? Till second order, we can easily find out the roots. But what do you do when you have a third order system, leave alone a higher order polynomial?